Hi, hello. Today, let's solve this lead code distinct subsequences problem. So let's try to read the problem and see what is it asking. So it says, so we have two strings S and T, return the number of distinct subsequences of S which equals T. Essentially, this problem is asking us to find the distinct subsequences that could form the given string T. Um, so let's take an example of what this is trying to say. So let's take a look at this example. So you have S, the given string S, and T. Okay. So all it's asking is how many subsequences are possible so that you could generate the T string from S. Uh, so you have, so let's take this example. So you have this S string BABG, and this is the T, which is BAG. Now you can see there are five possibilities of five subsequences possible. Like for example, you could pick the first B, the first A, and the last G. That is a match to the given string T. You can pick this B, this A, and this G from S, and that is a match to T. So in that way, you have five counts of distinct subsequences possible uh, from S to form the string T, right? So this is just a listing of all those five subsequences. So you can pick first B, first A, and last G. You can either pick first B, first A, and the third G. So uh, the T can be formed. Uh, yeah. So let's see. So let's see if we can find to rephrase the problem. Uh, just take another point of view. So it's asking for distinct subsequences, but you can think of this as an alignment. Like for example, you're trying to align S and T, and essentially trying to find how many such alignments are possible. So you can see this whole thing is one alignment where the first B matches with the first character in both S and T matches, A and A matches in both S and T, and there is like just blanks until G. In the same way, this is a second alignment where you have empty characters until this empty characters until the fourth character, and just B and G are filled. So you can think of these as different alignments instead of just thinking of as a sequence. Just try to think as an alignment. Um, so all we are trying to find is how many different types of such alignments are possible um, to get the final answer. Um, just try to let's see if we can get a recursive or any other way of solving this problem from this example. So you can see here the answer for this example which is given is 5, right? So those 5 are listed here. So if we just take a look at this problem, at this solution here, which is manually generated, so you can see uh, alignments ending at this position are equal to alignments that this G from S is contributing to or not. Like if you see in this last row, this particular G from S is not contributing to the final answer, which is 5, but the rest, it is the rest 4 solutions, this G is contributing to the count. So you can just think it as number of alignments, uh, possible alignment count is equal to alignments where G is present plus the alignments where G is not present. So let's try to write the just a fundamental or a basic English description of what we just find, what we just found. So like number of alignment equals to number of alignments where G is present plus number of alignments where G is not present. Not present, right? So how will you know number of alignments where G is present? And how will we know number of alignments where G is not present? So now this directly translates to the recursive equation. Let's say f of I comma j equal to f of I minus 1 comma j plus f of I minus 1 comma j minus 1. So here there are two conditions. So this is skipping the current character, in this example G, right? And here it's not skipping, it's skipping, yeah, skipping both the character from S and T. So this happens only if there is a match. And this is if there is no match, right? Yeah, so as you can see, there is this is a recursive problem, and let's see if we can find if there are any overlapping subproblems to ensure that it can be solved with a dynamic programming approach. So for that, let's see. So let's take a look at the same recursive example and try to substitute some values and see. So let's take the same example, which is G. Uh, so here, see, so the I and J are just the indexes of G here. So f of 6 comma 2 is just I just substituted the values, and f of 5 comma 2 and f of 5 comma 1. So you can see there are overlapping subproblems here. So f of 4 comma 1, f of 4 comma 1. So there are overlapping subproblems. So we could solve this problem using a bottom-up dynamic programming approach to ensure that we don't resolve or those repeated or overlapping problems. So let's try to code this solution with the information that we have. So I'm just creating a table like 2D. Okay, so let's see, and number of rows is equals to length of S, and number of columns equals to length of T, and the table equals to, I'll just let's initialize with zeros for now. Okay, rows, and for range, columns. So let's see if we need any base cases to solve this. I think for sure, like table of 0, comma 0, which we can make sure that it is 1 if S of 0 equals to T of 0, else it would be 0 for sure, right? Then we can think of another base case where if you're trying to align uh, the first column in our table would be, let's see, so for row in the range of comma rows, uh, table row 0 equals to 1 plus table of row minus 1 0 if if the character matches S of row equals to T of 0, then this is the case. Otherwise, else it is, I think it is just the previous one. Okay, yeah. Okay, or I think it would be just 0 instead of this. So what is our so before this, let's just take a look at what is our table of I comma j, like what is the value in each table represents. So it represents the number of alignments possible until I comma j, where I represents the index until s. So I represents the index of s, and j represents the index of the character in t. So we are essentially saying that, let's say you have let's say some I is somewhere here and j is somewhere here. So let's say this is a subproblem we are calculating. So we are essentially asking, like, are there any alignments or sequences that could be possible, like BA, BG, and BA? So do you have, so the answer from this problem, subproblem is how many alignments are possible so that you could align BA, BG to BA. So that is what we are trying to store in our table. So let's see, and then we have to iterate the rest of the table and fill our values. So for row in range of 1 comma rows, for column in, let's say, range of, I think, 1 columns. Um, okay, so in our recursive equation, there are two choices. Either we could include that character or not. Uh, so it's like table of, we're trying to fill ij, which is equal to okay, so there are two choices here. So I'm just creating a temp variable which is 0. So if s of row equals to t of col, which means there is a match, the character matches. So now we can ignore like temp equals to table of, from our recursive equation, which we have it earlier. So we can say row minus 1, column minus 1, but otherwise it's the earlier choice if it's possible, if it's available. Otherwise it would be 0. But the other value which we need is skipping the character, which is row minus 1, but not skipping the character from t, which is just the call. So okay, this should be row and column. So, and the return, we just have to return the final count, which stays at the bottom right of the table. So you can say just -1, -1. So let's see if this works. Okay, so there is some issue here. Okay, so rows, what is it? Okay, so I found the error. I think it's here. So this should be columns and this should be rows. Okay, so let's see if it works now. Yeah. Okay, so let me know your thoughts about this solution and about this approach. Thank you.